Hello, welcome to the video. Today we're going to be looking at this. Now I've got a couple of jumpers on here because I've been using it, but we can take them off. Let's have a look. So this is an FPGA board. It's based on the Cyclone 3 and it's actually a clone of the MIST, and it's called the MIST 1010 FPGA, and this is a PCBWAY share project. So let's just have a few words with them and be right back. We all know PCBWAY makes great quality PCBs. After all, the clue's in the name. But did you know they also have a lot of other specialist equipment to make your 3D designs a reality? PCBWAY can make your designs come to life with CNC rooted material made out of lots of different metals and plastics. They can make 3D prints, everything shipped straight to your door. They can even do vacuum forming and injection moulding. On top of this, PCBWAY has a great maker store where you can buy any components and equipment that you can imagine. All you need to do is get designing, get onto PCBWAY, and they'll ship it straight to your door. But that's not all. A lot of other people have done this, and they've made their own designs, and you can also replicate them. They're ready on their site to download, manufacture and send straight to you. If you're not the design type, no problem. Just look at their shared project. Someone's already made a design for you. All you got to do is click the button and have it sent straight to you. The answer's simple. If you want to make anything, check out PCBWAY. Okay, so here we go. This actually won a design competition, I believe, at PCBWAY, and they've sent me this and assembled it and everything, and this is as they've sent it, which is pretty damn good. Now you can see the size of my thumb. I'm not particularly large bloke, so you know, this is some fine soldering there, and as you can see, the quality of it is really good. We all know that PCBWAY make PCBs, and they do a lot of other stuff too, as you've just seen, but this was actually sent to me assembled. So yeah, the only real downside with this is they've assembled the front switch sort of on the wonk, and that's because the designer actually bends a leg out of the way, but I'll correct that, that's no problem. So as I said, this is a clone of the MIST, and it's made by someone called Eugene someone. I'll murder his last name. What is it? Lavoisier? Yeah, Lazavoy. Yeah, I'll put it on the screen. That's probably safer. And he's made it in a very small form factor, as you can see by the size of my hand. So yeah. So this has got all the same things that the MIST has got. There's a few extras as well, and it can take all the MIST cores as is. So there's no special messing around or anything like that. Bam! You can have one of these made, sent to you, and it won't take a lot to actually get going with it. So what we're going to do is we're going to have a look, and you're going to be wondering why an old FPGA system is still relevant today. And it's one of those things that is not readily apparent unless you know how these things work. So we're going to have a quick primer on the FPGA and how it works, and carry on from there. Okay, so we're going to talk about FPGAs, and this is going to be the most briefest skip over you've ever heard, because this is a massive subject, and I do mean immense. So the FPGA that we've got in this particular board is a Cyclone 3. It's quite an old FPGA now, as I think they're up to Cyclone 5, and it's an EP3C25, which is this one here. So as we can see, it's got 24,624 logic elements. Now a logic element is a bit of a funky thing, because it's not like a gate where it's and, or, nor, and that sort of thing. It's actually quite an intelligent unit. We'll come back to that in a minute. It's also got some M9K blocks. Now, M9K is a, how do I explain this? A type of memory, and it's unique to the Cyclone 3. I think the Cyclone 2 had M4K, and so on. It's a very strange thing, and again, we'll come back to that in a minute. So you've got a number of RAM bits, which is 608,000. Yeah, so it's around about 64K, I think, or 66K, or yeah. PLLs. This is the next thing, and a PLL is a very, very integral part to FPGAs because it's a phase lock loop. That means it's a clock, and it's a clock that can govern itself to stay within a very tight tolerance. Yeah, so as you can see, you've got 20 clock networks, and well, look at this, 215 user IOs. Hoorah! Anyway, this is the basic spec of the actual FPGA chip. Now, let's come down a minute. Yeah, this is going to get a bit funky. Not that one. Let's have a look at this. So, the logic array block, the lab, consists of 16 logic elements grouped together, and a lab-wide control block. An LE is the smallest unit of logic in a Cyclone 3. So, okay. When you write a program for an FPGA, it's in code, and it gets compiled into a logic map as such. So when people say, oh yeah, it's a bang-on reproduction of this machine or whatever, that's not necessarily true, because how that gets turned into the actual running logic is largely down to the compiler. So it's more of a behavior modeling, and I'll illustrate that in a minute. So here we go, M9K. Each M9K of the Cyclone 3 provides 9 kilobits of on-chip memory capable of operating up to 315 megahertz. That's pretty damn fast. So let's have a look. Blah 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 blah. Now what this is saying is M9K can be configured as ROM, RAM, dual ported. It can do some really funky things, and that's very well used in a lot of reproductions of retro machines, and I'm going to show you exactly why in a bit. It can do all sorts of funky stuff. So here we go, it's describing the clock networks, you see. So let's say that you generate a clock. With a normal program, each instruction is executed sequentially. In an FPGA, it's not. You've got to synchronize it. It's all going to try and run at once, so you've got to tie it to a clock. And that can be the rising edge, the falling edge, after a delay, yada yada yada. But once you've got a clock, you can do some funky things with it. You can clock divide it by performing maths on it. So you can have a clock running at 16 megahertz, and then you can divide it by 2 to give you an 8 megahertz clock, and that doesn't take anything else. You can use a logic element to do that. So you can write a little bit of code, and it will literally, every second clock, it will give you a pulse, and that gives you a, you know, an 8 megahertz decimation of your 16 megahertz clock. And you can do that all over the place. It's really quite funky. So if we switch to this, this is the code for the MIST C64 core. And like I said, I'm massively missing out. So much information is laughable. So this code's been around a long time. In fact, there's some of my actual comments in this code from 2017 still. But the RAM is one of the things that I'd really like to focus on, especially for retro machines, because like I said a minute ago, people say, oh yeah, FPGA, it's a bang on reproduction. It's not. It's a behavioral model. So here we are looking at the screen, and you can see some actual source code. It's not that bad to actually read. It's in VHDL, this particular one. And as you can see here, let's have a look at the kernel. This bit of code here. This creates an instantiation of an entity called work DP-ROM, and that's dual ported ROM. How can you have dual ports? That's a strange question, isn't it? Well, it's actually because it's an M9K block. Actually, with this being a MIST, it's not going to be 9K. It'll be the equivalent on the next Cyclone model. But the principle of what I'm saying is the same. So these RAM blocks, the B RAM, block RAM, people have got a lot of different names for it. They get bigger on different FPGAs. So for the Cyclone 3 that we're looking at here, you've got about 66K of this special type of memory. And you can divide that up how you want. For the MIST, you've got a lot more. I think Sorglik said 490K or something. It's laughable. And when you bust out the Mega 65, well, damn, that's got 1.8 megabytes, I think. It's absolutely laughable. Anyway, here we are with a Cyclone 3 on the MIST. And these blocks, you can tell it to read to it. And if you choose a dual ported one, you can read and write not only at the same time but at different speeds. Now, FPGAs are a very strange device. They don't know anything about anything. You've got to tell them every little thing, because once they start up, they can only run the bit stream that's been compiled for it. So if you want to talk to the outside world, normally you have what's called an HPS, which is a hard processing system. Now in the case of the MIST, it's an Arduino Mega. So this Arduino Mega is linked via I/O to the FPGA. So the Arduino Mega handles the devices that you plug in, like your keyboard, mouse, gamepads, joysticks, also your SD card, all that sort of stuff. Handles it all, apart from video. Video is a bit of a different matter altogether. That usually comes directly from the FPGA, and there's a lot of different reasons for that, and that's way beyond it. I'll be here all night talking about that. But basically the Arduino handles all that sort of stuff. So when you bring up the on-screen menu in the MIST and the MIST, what it does is it talks to the Arduino and says, right, get me this file from the SD card. Now, you trying to code up the file structure for FAT32 or something like that in logic is going to burn through a lot of logic elements, right? So it's easy to do it in regular code on an Arduino and have that manage it. That way the FPGA doesn't use any resource at all. All it says is, give me the code, give me the byte stream. So, I digress a little bit. Let's say you set up a dual ported RAM or ROM. It's both the same in this case, it's an M9K block. So basically it says, right, hard processor system, give me that file, and it shoots it into RAM. And then you can use it as ROM and read from it on the other port. No messing around. You look inside a Commodore 64, it's not dual ported. The ROM chip is just burnt already inside. You can't replace it. But on here, you can see you've got a write clock and a read clock, a write enable, your data lines, your write address, and your read address. Now, what comes out of it is sent to the core. Here. ROM data 64. Oh, I don't know why I've clicked that, never mind. So Q is your output. So basically this means that with a really simple construct, you could, all your ROMs and RAM you can create in block RAM and have the hard processor system inject a new piece of code into it while you're running. The same principle is used to load a PRG file. Although I think on the MIST, I think it may have changed a bit. Yeah, I think it may have changed a bit. You're using SD RAM for your actual 64 RAM now. But again, that turns into a bigger thing. But a lot of this works along very similar lines. And even though the 64 doesn't have this in it, this behaves and replicates the behavior more closely than anything else. If we come down, I can have a look. Oh, as you can see, some old comments from me in there. That was the Ultimax mode. I added that back in 2017 when a cartridge didn't work. Yeah. Yeah, this is only one part of it. The source code for this is massive, and it's written in a couple of different languages. So basically your FPGA consists of clocks, and let's see if this is your clock that will be generated. I can't, oh, it's been so long since I've looked at this. So clock 32 I think is your regular clock, if I remember correctly, 32 megahertz. And even though the 64 doesn't run at 32 megahertz, that is decimated down. It actually does this in quite a funky way on here, in that it's split into 32 cycles, and some of it's for the VIC, some of it is for CPU, as you can see here. So that's how they got around it. And the 64 does not work like that in the slightest, but it acts like it, and that's a very useful thing to keep hold of now as a notion. So your FPGA has all these clocks, it synchronizes them to them. You've got dedicated block memory, and you've got SD-RAM, which takes a bit of special handling, and it recreates how a machine behaves. Now because of that, and as you can see here, 32 megahertz is very slow. Let's have a look at the PLL. What's going on in here? This is Verilog, so this is a different type of language to VHDL. Here we go, look. So you've got 3 clocks here. The reference clock is 50 megahertz. This is on the MIST, remember. You got 47.2, 63, I think 63 is probably for the pixel clock. And you've got 31.57, and that's because the C64 doesn't work on 1 megahertz. It's a little bit less than that, it's 0.98. So if you times that by 32, I suspect you'll get a number very close to this. It won't likely be exactly the same as that, as PLLs can only, and the clock generator can only get you so close to it with this kind of resolution. But to be fair, when you're talking 6 digits past a decimal point, it ain't gonna matter. No one's gonna notice. So yeah. So my point is this: with an FPGA, even an old one like this, and to some regards a MIST, because I think there's a new model of that coming out, the code is getting better all the time, but it doesn't relegate the FPGA chip to the scrap heap. So as long as you don't go over the number of logic elements that you use, which are the most basic building block, I say basic, it's really a lot more than basic, then your FPGA will be as good today as the day you bought it. It won't go out of date. So the programs will get better to run on it, they'll be compiled, and it's not going to suffer from things that a computer does, or a Raspberry Pi. And that's because a Raspberry Pi and a computer has an operating system, and everyone knows that these get absolutely screwed up with all sorts of updates, extras, changes, patches. So you end up having to do more with the same hardware, whereas with an FPGA, you know what you've got, and it's exactly what you've got. You're not going to suddenly slow down. So that's a little bit of a rant now I've gone on, and a little bit of an explanation as to what goes on with an FPGA. It takes a code like this, it compiles it into a bit stream. You've got a little processor near it that actually controls loading of the cores, or the bit streams. And even though this is a very old FPGA now, Cyclone 3, it's still well worth it. I mean, we're coming up to what, 8 years old, and some of these cores, this is the MIST core for the 64, as I've just said, but this has been backported, and the latest changes are only a month old. So all the nice goodies that the really pucker programmers out there have put in are now appearing on the Cyclone 3. And if you want more than that, I mean, the Amiga core is superb. The Atari core, the Atari 8-bit core, phenomenal. These are really mature cores, so there's no reason to think, oh, that's a bit out of date, because FPGAs don't suffer with that. So yeah, it's a bit strange, and it's a little bit of a odd concept to get into. I wonder if we can see a logic element. I'm sure there's one, and let's pay, bloody hell. There you go, there's a logic element. So when I say it's basic, it's really not. There's a hell of a lot goes into it. So yeah, there's all sorts. These are symbolic views of how it works, but a logic element can do a lot more than just one logical thing, like be a gate. It can do all sorts of stuff. As you can see, it's got lookup tables, it's got memory, it's got clocks. It's complicated, and luckily you don't need to know anything about that. All you need to do is learn how to program Verilog and VHDL, and then whop, you can start doing what you like. The compiler will actually do the rest. This is the 1531, as you can see here. Clocks this, everything is done on these clocks. Now this is Verilog, which is a bit different to VHDL. As you can see here, always at positive edge of clock sys. Now clock sys is your system clock. So every time, i.e. always, clock sys, then LFSR, that's a linear shift register, isn't it? Yeah, okay. Anyway, every time it does that, it will do this, and it will load everything it does here, round and round and round and round. In fact, this bit here is all self-contained. You can see the braces on the end, so it actually does this command here every positive edge. These are assigned all together. You've got another one here, positive edge. You've got a begin and end down here, so you've got a little bit of logic to load in the mouse. The 1531 is a mouse module, so it's probably a dodgy one to show you. The RAM is this file here, and this is based on, I believe, the actual reference code from Altera. So really this is the RAM, and this is the instantiation you saw a little while ago. So init file, this is the file that's passed as a string from the hard processor system, or the Arduino, or at Mega. How wide it is, in this case, you got 14 bits and 8 bits wide. So the word natural means that's what it normally is. You can override it with the instantiation. So it's saying that you've got 14 bits, right, which is easily 16K. So 16K wide, 8 bits, I'll get this right in a minute, 16K long in memory space with 8 bits per byte. So as you can see here, the ports coming out in and out of it are the write clock, the write address, data, write enable, the read clock, the read address, the output, and the chip select. And then you've got an architecture determining how it works, and then you've got a little bit of logic determining about the output and how it's going to write. So you've got a read port and a write port. So it's just saying that on the write port you've got a process, and that process says on the rising edge of the write clock, then if the write enable is 1, then the RAM is presented to data, or rather data is presented to RAM. It goes that way, I believe, and that's that process. And then the read port is, as you read it back out, it's reading it out to Q0 here. So yeah, and it's being managed up here. So what it's saying is it'll be 1 unless the chip select's active, and then it'll be Q0. So while there's no chip select, it'll be 1, and that's it. So it's quite simple to understand the code. I say that given that I knew how to program it a bit back in 2017. Not so sure now. I'm starting to learn again with the Mega 65, but that is very, very much harder to get into. That's the AMD version. It's an Arctic 7 FPGA, and to be honest, the MIST and the MIST programming environment, the Quartus, is far nicer to use than that AMD one. Oh my god, that's just that's very, very hard going. Yeah. So anyway, I digress yet again. There's a little tiny speck of what these FPGAs are about. So yeah, I think I'll wrap that explanation up there. Right, so as we know, the FPGA doesn't work on a clock signal as in a Raspberry Pi or something like that, because with a Raspberry Pi you have to serially execute all your commands, and an FPGA doesn't. So the high gigahertz clock frequencies you get are simply not applicable to FPGAs. So you have what's called a PLL, and this is a phase lock loop, and that means that it creates a frequency, and if it drifts too far above or below, then it corrects it. And where electronics is concerned, as soon as things change temperature, clock signals tend to change with it. So a PLL has been used for a long time now. Back in the old days of analog synthesizers, you know, they had to tune them to a certain room's temperature, otherwise the frequency of the notes would drift, especially as they got warm. In the 80s and 90s you started to see PLL based radios and stuff like that before it went digital. So once you've got one of these, the fact that it's older than something like a Pi or something is irrelevant, because the cores are still being developed and they can still run just as well now as they did before. So let's say that you've got a Raspberry Pi and you've loaded it up with something. As the emulator gets better and more accurate, it has to execute more instructions, and that means that it's got less time to execute everything in that one frame of screen time, as it were. So let's say we'll talk about a Commodore 64 core, for example. If you've got an emulator, everything's got to be run in 1000 divided by 50 frames rather, which is what, 20 milliseconds a frame. That's right, isn't it? 20 times 50, yeah. So as the emulator gets more complex and it needs to emulate more and more devices and other bits and niceties, it's all got to fit within that one 20 millisecond time window to do everything for it to seem like a smooth emulation. And as the code improves, and there's many different reasons for it, but it tends to have to execute more code as time goes on. So emulators can tend to, especially ones that are marginal, they can tend to start to slow down as they get more and more improved. But because of the parallel nature of the FPGA, you can actually, everything is tied to these PLL generated clocks inside, and these are generally running at a handful of megahertz. So the fastest bit is usually the picture, the dot clock, and You know, these top out, I'm going off the top of my head now, about 150 megahertz for HDMI, I believe, something like that. I could be well off, but like I said, I'm going from memory. So, yeah. So if you've got an old 8-bit machine, the actual clock speed of the machine is going to be very low. The peripherals are going to be very low. So generally, you tend to have somewhere between 28 and, I don't know, 64 megahertz of speed, because everything else is done in parallel. So that means, and this is the important takeaway now, that means that you can actually use an updated core with no loss of speed. In fact, it gets better on an FPGA than it does on a regular type processor. Of course, this is not, you know, a universal rule. Some things get improved and actually speed up over time. There's many different facets to this, but broadly speaking, an FPGA, as long as you don't go over the logic units, it's still as good as the day you bought it. So the cores that have been on it are actually still been improved. Right now, even though the MIST is several years old, I mean, we're going back to 2015, I believe. The cores are still being improved. The 64 core has been backported from the MIST, and trust me, that is an absolutely spankingly good core. And that runs on here. Now, when you run that, you know, you're talking a seriously good level of, people that get the ump for call it emulation, but simulation, we'll call it that. And it's really good. And you're not going to know the difference between a real machine and this when you've got it going into a CRT screen. Obviously, I mean, I like HDMI personally, but yeah, that's the only real giveaway. And this can do a lot of different cores, and a lot of the cores are very good. Very, very good. Notable cores are the C64, the Amiga. Now the Amiga AGA is seriously getting a lot of attention as well. Both of those are extremely good on there and definitely worth some time. It's worth it just for those two cores. I believe the Atari ST is good, but I haven't really explored that a lot on the MIST line. I have a real MIST as well as a MIST-er, and yeah, I played it a bit on the MIST-er, but yeah. So the SNES and the Mega Drive are also really, really good on there. Really good. And then you've got some of the older cores that have not been updated for a while, but they haven't needed to be because they are good. And that is the Atari 2600 core and the Atari 800 XL line of computers. Works very, very well on there. Very well. So that's the use case for now. And this guy, I believe he's Ukrainian, who's designed this, has done an absolutely phenomenal job. Really has. And so has PCBWAY for making it. Apart from me having to straighten up this switch at the front here. But that's because where he's missed the hole there, you can see. So, but this is a share project, so anyone can have one of these built. And PCBWAY will take care of everything. They'll build it, send it to you. You know, all you've got to do when you get it is add your joystick ports to it. Now, it can use USB for joystick, but there's also two 9-pin headers on here. And you can see here, that's Joy 0 and Joy 1 here and here. And they can take two button joysticks, and you just come off their ribbon cables, and you'll see that on the share project page. But this is going to be the first of 3 videos, and I'll be showing you how to case it up and everything else later on anyway. But again, the quality is just fantastic. This is as good as an off-the-shelf product. Yeah, this is literally how it's appeared. I've powered it up, I've put the firmware on, and that's all I've done with it really. I've played a couple of games on it to make sure it works. But yeah, absolutely brilliant. So you've got all headers on here for JTagging, so you can get in and program everything up. Actually, programming the firmware on this was super easy. I used a program called Bossa, and I'll show you how to do that. And you just plug in via the micro USB for power, and it just sees it, uploads the firmware. You just choose it, download it first from the MIST site. Bam, jobs are good. There's tape input here. There's a physical power switch there. And yeah, that's really all there is to it. This port here is for a real-time clock, and PCBWAY supplied that as well. It's just one of those plug-in ESP modules, ESP Wi-Fi modules. So yeah, it's really nice. Really super impressed. And as you're going to find out later on, it's got a really nice output quality to it too. Now the MIST line of FPGAs, they can output regular VGA. I say regular, it's a bit weird because they use the VGA socket, but it's like a multi-use. So although it can output VGA, it can also output YPBR, well, yeah, component anyway. And it can also output RGB through this as well for a SCART. And that's what I've been using it with. And that's really nice quality. But this board has been designed to drop into an off-the-shelf G738 case, I believe it is. So yeah, he's done an absolutely bang-up job of it. So what I'm going to do is I'm going to show you how to load the firmware on, and we'll go from there. Programming using Bossa is really simple. All you need to do is go onto the MIST site, get the latest firmware, and it's a binary file, and then select Erase All and Boot to Flash in Bossa and connect it with a micro USB. Then just hit go, and that's it. Once you hit right, it just zaps it in there. Okay, so the video's gone on a bit longer than I would have liked. It's just an explanation of what I've received from PCBWAY, how it works, and the explanation's a bit wonky donkey, I know that. In the next couple of videos about this board, I'm going to show you the cores, especially the updates. Some of them are phenomenal, and we're going to get it into a case and actually make a completely finished unit. Now have a look at my compadres in the description. As before, they're all listed there. The difference now is they've got a Discord channel, and anyone can come along and be a member and join in a chat talking about retro stuff. It's really light-hearted, so give it a look. So many thanks to PCBWAY for sending me the board, especially Zoe, nice one girl, and I'll see you on the next one. Later.